In this video, I'm going to show you how I tested the differences between the sexes across brain size in order to show you where I estimated eta squared estimate of effect size. So here we have the sex variable here, 0s and 1s, and the sample size is 100. And I'm just going to quickly show you that 0 is female and 1 is male. And the dependent variable is brain size in kilograms. I also have brain size in grams here, but I did the analysis on kilograms to have smaller numbers to work with. So to analyze these data, I went into Analyze, General Linear Model, and Univariate, and I used this approach because this is the only way in SPSS that I know to get an estimate of effect size that's eta squared for a test of the difference between two means. So click on Univariate and put brain size kilograms in the dependent variable and sex as a fixed factor, which is the independent variable. And then click on Options, and we want the Descriptive Statistics, and we want estimates of effect size. And this is where we're going to get that eta squared that SPSS actually calls partial eta squared, unfortunately. Click Continue and click OK. And here are the descriptive statistics. We can see that the females had a mean kilogram brain weight of 1.27, whereas males had 1.47. And here are the standard deviations in the sample sizes. So numerically, males have a larger average brain size than females. I don't know if it's significant statistically yet. I have to look at this table here. If I look at the sex independent variable row, I've got an F of 50.91, and with 1 and 98 degrees of freedom, that is p less than 0.001, so I've rejected the null hypothesis of equal means. So statistically, I could say, with alpha specified at 0.05, that these means are different from each other statistically. Now here's the eta squared, 0.342, and this implies that 34.2% of the variability in brain size was accounted for by sex. Now SPSS calls this partial eta squared. It's a mistake. It's really just eta squared. Now most people would be accustomed to testing the difference between two means with an independent sample t-test, and you could do that, and you will get a t-value that is equal to the square root of 50.909. But you do not get the eta squared if you go the t-test route. And so that's why I did this in an analysis of variance framework, because it's going to allow me to compare relatively easily the result I'm going to get from ANCOVA, which is going to include body size as a covariate. And body size is an important covariate in this analysis because males and females also differ with respect to body size. Let me just show you that quickly. General Linear Model, Univariate, throw out brain size, and put in body size factor, and click OK. And here we can see females with a negative body size factor. So this is a factor score that was created on the basis of several body size indicators, and the males are positive. And we can see that there's quite a large effect size that's very obviously statistically significant with a whopping F value. So these two means are statistically significantly different from each other. Males have larger bodies than females. That's not a breakthrough scientific discovery. But the key part here is that it's quite a large effect size, 66.9. Maybe if I took body size into account, the difference between males and females in brain size would also reduce to non-significance and maybe even close to zero. That is the purpose of the analysis of covariance.